Hello viewers, welcome to video number 124 of the channel MALACHEMPHILIC. And this video is the 64th episode of Chemical Thermodynamics, where the topic is Clapeyron equation, concept, derivation and application. So let's start. See, Clapeyron equation gives the slope dp by dt of a two-phase equilibrium line on a pressure-temperature phase diagram of one component system. What does it mean? This is one component system, two phases. These phases may be solid liquid, solid vapor, liquid vapor, whatever it is. And on this line, these two phases are in equilibrium. That means every point on this line, the two phases are in equilibrium. And this plot is pressure versus temperature plot. Okay. And Clapeyron equation gives this slope dp by dt. That expression is given in the Clapeyron equation. So, know that for pure substance, 1 mole, that this chemical potential mu is equal to the molar Gibbs free energy. That I have told in my earlier video. This is number 1. And number 2, that phase equilibrium means two phases of a substance are in equilibrium means chemical potential of the substance in every phase should be same. So here these two phases are in equilibrium. This line indicates the equilibrium. That indicates that chemical potential of the substance in alpha phase must be equal to the beta phase. That means that mu alpha is equal to mu beta. And just now I have told that mu is equal to Gm. That means what can I write? Gm alpha phase is equal to Gm beta phase. And already I told you, I didn't write here. This equilibrium indicates anything. So solid and liquid in equilibrium, or this liquid and vapor are in equilibrium of a particular substance, of a pure substance, and then your solid in equilibrium with vapor, anything. Okay. Now suppose this Gm alpha and Gm beta, what I have written here, that is at point 1. That means at point 1 on this line, this Gibbs free energy or molar Gibbs free energy of the alpha phase I have denoted by Gm alpha and beta phase in Gm beta. And as on this line it is in equilibrium, so Gm alpha is equal to Gm beta. So this is for, I write for point 1. Right? Now, if you little bit change the temperature, say change it by infinitesimal small amount dt, okay, then system will readjust itself, and then while readjusting, pressure also will change. So pressure also will change by the small amount dp. Okay, so if I draw a line from here and here, so pressure change will be this much, that is dp. And once again, after reaching to this point 2, there will be readjustment, pressure also will change, and at the same time this molar Gibbs free energy also will change, and it reaches to the point 2 where once again it is in equilibrium. So at point 2 also this chemical potential or the molar Gibbs free energy of the two phases will be same. Now suppose when it has moved from point 1 to point 2, then change in the Gibbs free energy in alpha phase will be dg alpha and beta phase is dg beta. So what can I write? At point 2, Gm alpha plus this change part, that is dg alpha, is equal to Gm beta plus this dg beta, that is at for point 2. So point 2 once again it is in equilibrium. So this is the condition. Now already we have written that since G alpha or Gm alpha is equal to Gm beta, so therefore what can I write? That is dg alpha is equal to dg beta. Right? We can write these things. Now we'll go to the next slide. we know that for single phase system, single phase pure component, pure substance, single phase pure substance, we know this equation dG is equal to VdP minus SdT. Already I have derived all this equation in my earlier video, plus mu and dN, only one substance to mu and dN. In place of mu I can write GMdN. Now Gm is equal to molar free energy will be equal to G by N. So what can we write? Ngm is equal to G. Now if I differentiate this equation, differentiating, what we will get? G will be is equal to this differentiation, first function differentiation of the second, plus second function differentiation of the first. We can write these things. So this is dG. Now look at here, this is also dG, this is also dG. These two equations we can equate it. So therefore, what can we write? We can write NdGm plus GMdN is equal to VdP minus SdT plus GMdN. So this GMdN gets cancelled, right? Now from here, see dGm is equal to V by N dP minus S by N dt. So therefore from here, what can I write? dGm is equal to V by N means molar volume. So VmdP minus, this is molar entropy. So Sm dt I can write. So remember this equation. dGm is equal to VmdP minus Sm dt. So once again I'll write here. This dGm is equal to VmdP minus Sm dt. Right? Now I apply this equation for alpha phase and beta phase. So for alpha phase, what it will be? That is dGm alpha, that will be is equal to Vm alpha dP minus Sm alpha dt. This is for alpha phase. Okay. And for beta phase, what it will be? dGm beta is equal to Vm beta dP minus Sm beta dt. This is for beta phase. Right? Now at equilibrium, this will be same. Already I have proved that dG of alpha, dGm alpha phase is equal to beta phase. So therefore at equilibrium, this Vm alpha dP minus Sm alpha dt, that is equal to Vm beta dP minus Sm beta dt. Right? So now all this dP part, if we bring together, so Vm alpha minus Vm beta, and this is dP, and that is equal to Sm alpha minus Sm beta, entropy of beta phase, into dt. Right? So therefore from here I can write dP by dt, that is equal to this Sm alpha minus Sm beta divided by this Vm alpha minus Vm beta. So this I can write it as delta Sm molar change of entropy in the phase transition. Here phase transition will be from beta to alpha phase because final minus initial we consider, no? So beta to alpha phase. This one divided by delta V M, that is the change in the molar volume for the phase transition beta to alpha phase. Okay, and then I can write it as that this next slide I'll write. I can also write dp by dt, that is equal to delta S by delta V. I can write it. Okay. Now we know that for reversible phase transition, what we know that entropy change delta S, that will be is equal to enthalpy change during that process delta H divided by T. Entropy change, that is equal to change of enthalpy divided by T. Okay, so if I put it in this equation, then what it will be? dp by dt, that will be is equal to delta H divided by T delta V. Okay, and delta H, that is the heat absorbed or heat released. See here it is heat absorbed at constant pressure. So this I can write it as Q divided by T delta V. Right? So this is your Clapeyron equation. Even this one is also your Clapeyron equation. So this equation, say this is number 1 and mainly this one, number 2, this is your Clapeyron equation. Clapeyron equation. Right? So, Clapeyron equation is dp by dt is equal to delta H by T delta V, or in place of delta H, if I write Q by T delta V, this is the Clapeyron equation. As I told you, this is also, here also I write, this is also Clapeyron equation. Okay, these are the forms. Now, if we look at here in this Clapeyron equation, this delta S is the entropy change during phase transition from beta to alpha phase, and delta V is the volume change during phase transition beta to alpha phase. If for the phase transition we consider alpha to beta phase, then what will happen? Both the sign will change, but quotient will remain same. Understood? If we consider the alpha to beta phase transition, then only this sign will change, delta S sign and delta V sign, but overall quotient remains unchanged. Okay? So this is your Clapeyron equation. Now we'll see the application of it. So application of Clapeyron equation for solid liquid. It is used to study the effect of pressure on melting point. That means how melting point changes with rise in the pressure. Right? So just now we have seen this Clapeyron equation dp by dt, that we have seen that delta H, if I consider the molar enthalpy change, so delta Hm divided by T delta Vm. We have seen this one. Okay. Now delta Vm is the, what is that? I have considered solid to liquid phase. That means this is a fusion. Solid to liquid equilibrium means phase transition means that is the fusion. So here this delta Vm will be what it will be? That is volume of the liquid phase minus volume of the solid phase. So here it will be delta Hm I can write divided by T. Here I can write this volume of the liquid phase, everything I am considering molar, minus volume of the solid phase. Now when this VL is greater than, volume of the liquid phase is greater than volume of the solid phase, right? Then what happened? Then this part will be positive. This part will be positive means then this dP by dt, that will be your positive. dP by dt positive means if you increase the temperature, that means plus dP, then plus dP. If you increase the pressure, that is plus dP, then temperature also will increase. What is this temperature? This is melting point, or here I write fusion temperature. This is also delta H fusion. Okay, so if you increase the pressure, then this temperature, that means the melting point will increase. So when VL greater than Vs, then with increase in pressure, the melting point increases. Okay, increases. Now when this VL is less than Vs, say for example your ice. Okay, the volume of the ice is more. So this is ice. In that case, what will happen? If VL is less, then your dP by dt, that will be is equal to negative. If it is negative, that means if you increase the pressure, this should be negative, otherwise overall negative will not come. Then this melting point decreases. In that case, what will happen? With increase in pressure, the melting point decreases. Melting point will decrease. Okay, because this is negative. If you increase this one, melting point will decrease. Right? So this is the effect. That means we can study the effect of pressure on the melting point. This is the application. Okay. Now we'll see the problem. So problem number 1, calculate dt by dP for the ice water system at 0 degree centigrade. Delta H fusion for water they have given, that is 6007.8 joules per mole, and they have given the conversion factor 1 joule is equal to 9.87 10 to the power minus 3 dm³ atmosphere, and molar volume of water they have given 18 centimeter cube and ice 19.63 centimeter cube. Right? So this molar volume of water, that is, we have to take it into dm³. That means we have to divide by 1000. That means 0.018 this much dm³. Okay, this is the molar volume of water. Now this molar volume of ice, now we write molar volume of ice. Molar volume of ice, this is equal to 19.63, no? So 0.01963, that is dm³ mole inverse. Mole inverse, here also dm³ mole inverse. Right? Now this we'll put it in the equation now. Here it is dt by dP. Clapeyron equation, that was dP by dt. So we have to write it the reverse way. So it is dt by dP. dt by dP will be is equal to your temperature, then this volume change, that is VL minus Vs, and divided by this delta H enthalpy of fusion, that is delta H fusion. Okay, so What is the temperature? 0 degree centigrade. That means 273. And what is the molar volume change? Molar volume change is liquid is 0.018 minus 0.01963. Okay, divided by what is delta H fusion? That value is 6007.8. You have to convert it. That means into 9.87 into 10 to the power of minus q. You just look at this unit also. Okay, so these are the things. Now, if you calculate it, then the value will come 0.0075 Kelvin atmosphere inverse per atmosphere. Okay. Now look at here. This is dmq mole inverse. So here dmq mole inverse, right? Now here it is dmq atmosphere. This part dmq atmosphere, and here it is again mole inverse was there. So mole inverse here, mole inverse, dmq get cancelled. Here atmosphere was at the denominator. Okay, and temperature has been at the numerator. So Kelvin atmosphere inverse. So what does it mean? And this is, it should be negative because 0.018 minus this thing. So I should put the negative sign. So what does it mean? Therefore, what we can write? The melting point of the ice, melting point of the ice decreases or decreased by 0.0075 degree per increase of pressure of 1 atmosphere, or with every 1 atmosphere increase of pressure. Okay. So this is the things. Melting point of the ice decreased by 0.0075 degree with every 1 atmosphere increase of pressure. Right. Now next one, volume change in a phase transition is 0. Okay. From this we may infer that the phase boundary is. What is our Clapeyron equation? That is dP by dt, that is equal to delta H divided by T delta V. Now delta V is 0. So it is, if delta V is 0, that means delta H divided by 0, that means it is equal to infinity. Slope means the tan theta. Tan theta infinity will be, when tan theta will be infinity? At tan 90 degree. We know that tan 90 degree, tan 90 degree, this value is infinity. Okay. Therefore, this angle must be 90 degrees. So, this is the right representation, right curve. This is 90 degree. Tan 90 degree will be infinity. Okay. So, these are the few questions on Clapeyron equation. Okay. Hope you have understood. Thank you.